We know that the basic building blocks of matter contains 6 leptons, 6 quarks and 4 force carriers and also Higgs bosons. In the previous lecture, we have discussed the essential characteristics of leptons, their interaction and lifetime. We have seen that certain leptons are extremely stable, whereas some of them decay with a lifetime of 10 raised to minus 6 or 10 raised to minus 13 seconds. The influence of lepton number in the decay process is also discussed in the previous lecture. Now we are entering into the realm of strong interaction physics. Six distinct types or flavors of spin half quarks are now known to exist. Like the leptons, they occur in pairs or generations up, down, charm, strange, top, beauty. Each generation consists of a quark with charge plus 2 by 3 and minus 1 by 3 in units of E. The quantum numbers associated with S, C, B, and T quarks are called strangeness, charm, beauty, and top respectively. The anti-quarks are denoted with charges plus 1 by 3 D bar, S bar or B bar and minus 2 by 3 U bar, C bar, T bar. Approximate quark masses are given in the table shown in next slide. Except for top quark, these masses are inferred indirectly from the observed masses of their hadron bound states together with models of quark binding. The stability of quarks in hadrons, like the stability of protons and neutrons in the atomic nuclei, is influenced by their interaction energies. However, for S, C, and B quarks, these effects are small enough for them to be assigned approximate lifetimes of 10 raised to minus 8 to 10 raised to minus 10 second for the S quark and 10 raised to minus 12 to 10 raised to minus 13 second for bottom and uh, both, uh, both, both C and B quarks. The top quark is much heavier than the other quark and its lifetime is of the order of 10 raised to minus 25 seconds. The lifetime is so short that when top quarks are created, they decay too quickly to form observable hadrons. In contrast to their other quarks, our knowledge of the top quark is based entirely on the observations of their decay products. When we talk about the decay of quarks, we always mean that the decay takes place within a hadron with the other bound quarks acting as spectators, that is, not taking part in the interaction. Thus, for example, in this picture, uh, neutron decay at the quark level is given by the Feynman diagram and no free quarks are observed. Note that it is assumed that the exchange particles interact only with one constituent quark in the nucleus. The properties of 6 quarks are given in this table. Up, down, strange, charm, top and bottom. All have spin half and masses are given in units of giga electron volt by c square. The antiparticles not shown in the sphere have the same masses as their associated particles, but the electric charges q are reversed in sign. The last column shows the major decay path of this quartz. A particle by its nature is a localized entity. In classical particle mechanics, we are typically interested in calculating its position as a function of time xt, yt, zt. A field, on the other hand, occupies some region of space in the field theory. Our concern is to calculate one or more functions of position and time phi I, x, y, z, t. It is a good fiction to visualize that God has created field or particles or both and then space for their existence. The quantized field gets agglomerated to small and large particles that are grouped into families of photons, leptons, mesons, and baryons, which come from the two subgroups of bosons and fermions corresponding to 1 and 1/2 integral spins respectively, like males and females of a species. These then combine to heavier mass atoms, molecules, the matter, and finally the universe. This story sounds exciting, but physics or science needs reasons for everything why and how. Men create laboratories to test every possibility and reproduce the results to confirm and theorize through mathematical models and equations. Experimental evidence for the existence of quarks on the top of a hypothesis for performing convenient mathematical calculations is an example where the story turns into a reality. Both leptons and baryons are fermions, whereas photons and mesons are bosons. Mesons and baryons are the particles that participate in strong interactions and are collectively known as hadrons. They also interact through weak and electromagnetic forces, though such effects can often be neglected compared to the strong interactions. Leptons, on the other hand, experience no strong interactions and but interact through weak electromagnetic and gravitational forces only. In this lecture, we will try to explain the answer to a few questions like how does strong nuclear force charge independence? Why do they have short range? How does the range of nuclear force affect the stability of a nucleus? We will also discuss an interesting property of the neutron, which is stable inside a nucleus but decay in about 611 seconds if left let free. And many more questions to understand the fundamentals of high energy particle physics, including how and why the nuclear force is charge independent while strongly depends on nuclear spin. Even before describing more experiments to study the force between two nucleons, we have guessed a few properties of the nucleon-nucleon force. At short distance, it is stronger than the Coulombian force, and the nuclear force can overcome the Coulombian repulsion of protons in the nucleus. At long distance, of the order of atomic size, the nuclear force is negligibly feeble, and interactions among the nuclei in a molecule can be understood based only on Coulombian force. Some particles are immune from the nuclear force. For example, there is no evidence from the atomic structure that electrons feel the nuclear force at all. In other words, the electrons orbiting in an atom around the nucleus experience no influence of nuclear force, not only because they are far apart, but leptons are immune to strong force. As we begin to do experiments to explore the properties of nuclear force, we find several remarkable characteristics. The nucleon force seems to be nearly independent of whether the nucleons are neutrons or protons, and this property is called charge independence. The nucleon force depends on whether the spins of the nucleons are parallel or antiparallel, that is, spin dependence of strong force. The nucleon force includes a repulsive term, which keeps the nucleons at certain average separation. Otherwise, nucleus would have collapsed further. It has a non-central or tensor component. This part of the force does not conserve orbital angular momentum, which is a constant of motion under central force. The strong force increases with the distance comparable to nuclear dimensions. A deuteron or 2s nucleus consists of a neutron and a proton. A neutral atom of deuteron is known as deuterium. It is the simplest bound state of nucleons and therefore gives us an ideal system for studying the nucleon-nucleon interaction. For nuclear physicists, the neutron should be what the hydrogen atom is for atomic physicists. Just as the measured series of electromagnetic transitions between the excited states of hydrogen led to the understanding of the structure of hydrogen atom, so should the electromagnetic transitions between the excited states of the neutron lead to the understanding of nuclear structure. Unfortunately, there are no excited states for the neutron. It is such a weakly bound system that the only excited states are unbound systems consisting of a free proton and a neutron. The binding energy of the neutron is a very precisely measured quantity which can be determined in different ways. The binding energy of a nucleus is the difference in mass energy between a nucleus H and its constituent Z protons and N neutrons. B equals ZMP plus NMN minus MX minus ZME into C square. Grouping the Z protons and electron masses into Z neutral hydrogen atoms, we can rewrite the above equation as B equals Zm plus Nmn minus Mx into C square, with the masses generally given in atomic mass units. It is convenient to include the unit conversion factor C square with the definition that C square equals 931.5 MeEV by U. In the first method, we consider the molecules C6H12 and C6D6 and C5D12 and C6D6. The calculated values are in good agreement, and using the measured 1s and neutron masses, we can find the binding energy equals 2.22463 plus or minus 0.00004 MeV. We can also determine this binding energy directly by bringing a proton and a neutron together to form 2H and measuring the energy of gamma ray photon that is emitted. That is 1H plus N gives 2S plus gamma. A third method uses the reverse reaction called photodissociation. Gamma plus 2S gives 1S plus N, in which a gamma ray photon breaks apart a neutron. The minimum gamma ray energy that accomplishes this process is equal to the binding energy corrected for the recoil of the final products. The observed value is 2.224 plus or minus 0.002 MeV is in good agreement with the mass spectroscopic values. We know that the average binding energy per nucleon is about 8 MeV for most of the cases. Neutron is therefore very weakly bound state compared with the typical nuclei. Let us see how we can analyze this result to study the properties of neutron. To simplify the analysis of the neutron, we will assume that we can represent the nucleon potential as a three-dimensional square well as shown in figure. Vr equals minus V0 for small r less than capital R and equal to 0 for small r greater than capital R. This of course an oversimplification, but it is sufficient for at least some qualitative conclusions. Here, small r represents the separation between the proton and the neutron. So, capital R is in effect a measure of the diameter of neutron. Let us assume that the lowest energy state of the neutron has L is equal to 0. For each potential Vr, all we need to do is to find a solution of the radial equation minus h cross square divided by 2m d squared r by dr square plus 2 by r dr by r dr plus vr plus L into L plus 1 h cross square divided by 2mr square multiplied by capital R equals E into R. If we define the radial part of psi r as ur by u, then the above equation can be written as minus h cross square divided by 2m d square u by dr square plus vrur equals eur. This expression looks exactly like the one-dimensional wave equation and the solution can be written accordingly. For r less than r, ur is equal to a sine k1r plus b cos k1r, with k1 equals root of 2m into e plus v0 by h cross square, and for r greater than r, ur equals c into e to the power minus k2r plus d into e to the power plus k2r, with k2 equals root of minus 2me by h cross square. To keep the wave function finite for r tends to infinity, we must have d equals 0. And to keep it finite for r tends to 0, we must have b equals 0. Xi depends on ur by r as r tends to 0. Ur also must go to 0. Applying continuity conditions on u and du by dr at r equals capital R, we obtain k1 cot k1 r equals minus k2. This transcendental equation gives a relationship between V0 and capital R. From the electron scattering experiments, the RMS charge radius of the deuteron is known to be about 2.1 femtometer, which provides a reasonable first estimate for capital R. Solving these equations numerically, the result is V0 equals 35 MeV. This is actually quite a reasonable estimate of the strength of the nucleon potential even in more complex nuclei. Note that the proton and the neutron are very likely to be found at separations greater than capital R. We can see from this figure how close the deuteron is to the top of the well. If the nucleon force were just a bit weaker, the deuteron bound state would not exist. We are fortunate that it does, because the formation of deuteron from hydrogen is the first step not only in the proton-proton cycle of fusion by which our sun makes its energy, but also in the formation of stable matter from the primordial hydrogen that filled the early universe. If no stable two nucleon bound state existed, we would not be here to discuss this. The neutron wave function is shown in figure 4.2. The weak binding means that psi r is just barely able to turn over in the well so as to connect at r is equal to capital R with the negative slope of decaying exponential. Nucleons, like electrons, have spin quantum numbers equal to half. A nucleon moving in a central potential with orbital angular momentum L and a spin S has a total angular momentum J equals L plus S. The total angular momentum J behaves in a manner similar to L and S, and the magnetic quantum number Mj equals Ml plus Ms equals ml plus or minus half. Since ml is always an integer, mj must have half integral values only. The total angular momentum I of the deuteron should have three components: spin Sn and Sp associated with the neutron and proton respectively, and the total orbital angular momentum L of the nucleons, that is I equals Sn plus Sp plus L. When we solved the Schrodinger equation for deuteron, we assumed L equals 0 in analogy with the lowest bound state in hydrogen. The measured spin of deuteron is I equal to 1. Since the neutron and proton spins can be either parallel or anti-parallel, there are four ways to couple Sn, Sp and L to get total value for I equal to 1. That is, Sn and Sp parallel with L equal to 0, Sn and Sp anti-parallel with L equal to 1, Sn and Sp parallel with L equal to 1, and Sn and Sp parallel with L equal to 0. However, we take the value Sn and Sp parallel with L equal to 0. Along with the nuclear spin, the parity is also used to label nuclear states. The parity can take either plus for even or minus for odd values. If we knew the wave function of every nucleon, we could determine the nuclear parity by multiplying together the parities of each of the A nucleons, ending with a resultant pi either plus or minus. That is, pi equals pi 1, pi 2, etc. pi a. However, in practice, no such procedure is possible, for we generally cannot assign a definite wave function of non-parity to every nucleon. Like the spin I, we regard the pi as an overall property of the whole nucleus. It can be directly measured using a variety of techniques of nuclear decays and reactions. The parity is denoted by plus or minus superscript to the nuclear spin as I to the power pi. There is no direct theoretical relationship between I and pi. For any value of I, it is possible to have either pi equals plus or pi equals minus. By studying the reactions involving neutrons and the property of photon emitted during the formation of the neutrons, we know that its parity is even. We know that the parity associated with orbital motion is minus 1 to the power L, even parity for L equal to 0 or S state and L equal to 2 for D states, and odd parity for L equal to 1 for P states. The observed even parity allows us to eliminate the combinations of spin that include L equal to 1, leaving L is equal to 0 and L is equal to 2 as possibilities. The spin and parity of the deuteron are therefore consistent with L is equal to 0 as we assumed, but still we cannot exclude the possibility of L is equal to 2. We discussed earlier the spin and orbital contribution to the magnetic dipole moment. If L is equal to 0 assumption is correct, there should be no orbital contribution to the magnetic moment, and we can assume the total magnetic moment to be simply the combination of the neutron and proton magnetic moments, that is mu equals mu n plus mu p equals gsn mu n divided by s cross into sn plus gsp mu n divided by s cross into sp, where gsn equals minus 8 to 6084 and GSP is equal to plus 5.585691. We take the observed magnetic moments to be the Z component of mu when the spins have their maximum value equals half S cross. Mu equals half into mu n, GSN plus GSP equals 0.8798804 mu n. The observed value is 0.857436 plus or minus 0.000000 6 zeros followed by 4 into mu n, which is in good agreement with the calculated value. Still there is a small difference, and this discrepancy can be ascribed to the any number of factors such as contribution from the meson exchanged between the neutron and proton. In the context of the present discussion, we can assume the discrepancy to arise from a small mixture of d state L equal to 2 in the neutron wave function, or xi is equal to as psi L equal to 0 plus ad psi L equal to 2. The fact that neutron has an electric quadrupole moment q means that its probability density function is not spherically symmetrical. This immediately tells us that the nucleon potential, which specifies the force acting between the two nucleons, is itself not spherically symmetrical. The point is that all spherically symmetrical potentials have L equal to 0 eigenfunctions for their ground state, and the probability density function for such eigenfunctions are all spherically symmetrical. For example, the Coulombian potential and spherically symmetrical ground state of a one electron atom, but the observed departure from spherical symmetry is not too large. Thus, we consider neutron as a system in which the nucleons are bound in the 3s1 state of a spherically symmetrical nucleon potential Vr, where r is the distance between their centers. This potential specifies the force acting between two nucleons. This agrees with the fact that neutron is observed to have no bound excited states. Now, the spins of the proton and the neutron are essentially parallel in a 3s1 bound state of the neutron. We know that there are no bound neutrons with the nucleon spins essentially anti-parallel. What is the reason for the absence of a 1s0 state? An explanation is that the nucleon potential is spin dependent, being appreciably weaker when two nucleons interact with essentially anti-parallel spins in a singular state. If the potential is sufficiently weak to prevent the nucleons from binding stably together, the absence of 1s0 bound state is clear. In other words, only parallel spins provide sufficient potential to hold the nucleons together. Quantitative description for the spin dependence of the nucleon potential is obtained from the analysis of the scattering of unbound neutrons from protons. This quantitative information about the spin dependence is confirmed by analyzing scattering of low energy protons from protons, and that analysis also provides additional evidence that the nucleon potential is charge independent, that is, it makes no distinction between protons and neutrons. The evidence is that a nucleon potential which agrees with the measured neutron-proton scattering cross-section also agrees with the measured proton-proton scattering cross-section. This does not mean that the cross-sections are the same. In proton-proton scattering, the Coulomb potential which is present in addition to the nucleon potential affects the small angle scattering, and the exclusion principle affects all the scattering by suppressing certain quantum states. The scattering of a low energy nucleon from a nucleon does not give information about the form of the nucleon potential. Thus, only high energy nucleons have enough resolving power to be effective as probes in studying in the form of the nucleon potential. For example, if the radius of the potential is taken as 2 Fermi, the differential cross section for scattering d sigma by d omega can be expected to depart from isotropy when the kinetic energy of the incident nucleon exceeds about 40 MeV. Two nucleons interact with the nucleon force of range R equal to 2 Fermi in a state in which the angular momentum quantum number assumes its maximum possible value. If this value is L max is equal to 1, the kinetic energy of the nucleon in the center of mass frame of reference can be calculated as follows. We know that capital L is equal to root of L into L plus 1 S crossed with L is equal to L max is equal to 1, that is L is equal to root 2 H cross. Also, we have L is equal to P R prime, where P equals L by R prime equals root 2 S cross by R prime is the momentum. The kinetic energy of each nucleon in the center of mass frame is K is equals P squared by 2m equals 2 H cross square divided by 2mr prime square is calculated to be 1.6 into 10 to the power minus 12 joule or nearly 10 million electron volts. The total kinetic energy in that frame of reference is 2K equals 20 MeV. From the elementary mathematics, we have the two interacting particles of the same mass, the kinetic energy of the moving one in a frame of reference in which the other one is initially stationary is twice the total kinetic energy in the center of mass of the frame of reference. Thus the kinetic energy of the incident nucleon equals 40 MeV. So, the nucleon in the nucleus actually interacts strongly with each other only half of the quantum states that angular momentum considerations would otherwise allow to contribute to the total interactions. This property of the nucleon potential helps make nucleon forces saturate by suppressing the attractive nucleon forces in half of the interactions. But this is not enough to obtain a saturation. It is necessary that some of the nucleon forces must be repulsive. That is, there must be a repulsive part in the nucleon potential. The study of the proton-proton scattering at high energies showed that the radial dependence of the nucleon potential is such that it is a repulsive region It has a repulsive region in the center. Experiments on the scattering of high energy electrons from neutrons provide completely independent evidence of the existence of a strong repulsive core in the nucleon potential. The experiments show that there is a hole in the center of the neutron charge distribution. This means that the proton avoids the center of the neutron, presumably because of the very strong repulsion it feels if it tries to get too close to the neutron. Analysis of both the electron, neutron and proton scattering experiments indicate that the radius of the repulsive core is about 0.5 Fermi. The effect of a repulsive core potential on the radial dependence of the radial coordinate r and the radial part of the eigenfunction RR for L equals 0 state eigenfunction for high energy proton scattering is shown in the figure. The solid curve shows small r into capital R in the presence of the potential, and for comparison the dashed curve shows what it would be like in the absence of the potential. Because the energy of the incident proton is large compared to the depth of the attractive region of the potential, the effect of the repulsive core dominates and R into R is pushed out. In the second figure, the effect of the repulsive core potential on RR for L equal to two state eigen function of high energy proton scattering is shown. The solid curve, as in the previous case, shows smaller in the capital R in the presence of the potential, and the dashed curve shows what it would be like in the absence of the potential. Since R into R is negligibly small at the core radius, even in the absence of the potential, because of R into R is proportional to small r, the effect of the repulsive core is negligible. Thus, the attractive region dominates and RR is pulled in. The repulsive core in the nucleon potential is the most important factor responsible for the saturation of the nucleon force. In a nucleon, the core in the nucleon potential add large positive contributions to the total energy if the nucleons are too closely packed. That is why the nucleons maintain an average center to center spacing given by the measured nucleon mass density of about 1.2 Fermi. At this spacing, any one nucleon can interact only with a limited number of nucleons, since the range of the nucleon force is about 2 Fermi, and so the nucleon force saturates. If there were no repulsive region in the nucleon potential, the attractive regions would cause nucleons to collapse until its linear dimensions were about equal to the range of the nucleon force. Then each nucleon would interact with all other nucleons, and the binding energy per nucleon equals delta E by A would be approximately proportional to atomic mass number. Thus, we summarize the ground state of the neutron by the following parameters, which are measured quantities. Binding energy delta E is equal to 2.22 MeV, spin equals 1, parity is even, magnetic dipole moment mu equals plus 0.857 mu n, electric quadrupole moment Q equals plus 2.7 multiplied by 10 to the power minus 31 meter square. charge distribution half value radius A equals 2.1 for me. We have presented certain properties of nucleon forces that are observed experimentally. However, the theory was used essentially to correlate the experimental observations and not to explain their basic origin. There is a theory that is successful in explaining how certain properties of nucleon forces arise from more fundamental attributes of nature. The theory is known as meson theory, which originated with the work of Yukawa in the year 1935. Yukawa proposed that a nucleon frequently emits a particle with an appreciable rest mass called pi meson or pion. This particle hovers near the nucleon in the so-called pi meson field for a very short time and then is absorbed by the nucleon. Such a pion is called a virtual particle because it has a very short existence limited by its violation of mass energy conservation. If two nucleons are close enough for their meson field to overlap, it is possible for a pi meson field to leave one field and join the other without permanently changing the total energy of the system of the two nucleons. In the interaction, momentum carried by the pi meson is transferred from one field to the other and therefore from one nucleon to the other. But if momentum is transferred, the effect is the same as if a force is acting between the nucleons. According to Yukawa, the exchange of a virtual pion between two nucleons leads to the nucleon force acting between them. Quantum electrodynamics shows that the long range of the Coulomb force is a consequence of the zero rest mass of the photons. Yukawa adapted the theory to the case of two nucleons interacting with a short-range nucleon force by assuming that the particle exchanged has a non-zero rest mass. When he made this proposal, pions had not detected, but Yukawa was able to estimate the rest mass that agree with the observed range by performing calculations.